All right, welcome back. So today our mathematician spotlight is Edgar Duéñez. He's a senior software engineer at Google. When he was growing up as a kid in Mexico, he did a bunch of math contests, like the International Math Olympiad, and then he did a math major for undergrad, and then a PhD in computer science. Then he worked at a bunch of places, including Harvard, and throughout all this, the PhD and the stuff after PhD, he was studying search algorithms and evolutionary basis of social behavior from a computer science perspective. And now he works at Google, where he's developing machine learning for images. So you know, like, image recognition is a big deal, right? When you upload a photo to Facebook, it asks you if these are your friends, and it's usually right, which is a little, yes? Yes, and this didn't happen. Like 10 years ago, this did not happen, and it does now. And so that's a big deal. And I think he's not working on that exactly. It says he's working on like machines figuring out how useful an image might be to you. So it's a slightly different problem, but also important. All right. Good. So the last couple of days, so today and the rest of the time, we'll be talking about vector surface integrals. So this is like if you have a surface, like you imagine a net or something, and then you have a vector field flowing in the region of your surface, like you imagine a flowing stream with lots of little fish in it. You want to know how much the vector field is flowing through your surface, which you come up, it's called the flux of the vector field over your surface, or you can imagine it like how many fish you catch or lose or whatever. So today we'll do more surface integrals. And we'll also talk about Stokes Theorem, which relates vector surface integrals to vector line integrals, just like Green's theorem. So Green's theorem, you might remember. So I'll now tell you like how Green's theorem and Stokes theorem are related. So Green's theorem, you had, here's the plane. It was just a two-dimensional thing. So we had some region of the plane, here it is, with its boundary curve oriented counterclockwise, and we related something about the vector field, like the derivative of the vector field in the interior, to something like a line integral of the vector field on the boundary. And Stokes' theorem is exactly the same idea, except you imagine this region, which is living in two-dimensional space, like a comic character. Comic characters, like Snoopy or whatever, they live in two-dimensional space. But you take this and you say, oh, look, 3 dimensions. You lift it up and out. So you imagine you can take this same region. We've lifted it now into 3-dimensional space as like this little balloon membrane. And now what we're allowed to do is blow on it so that it becomes a curved surface. So for instance, if you blew on it, it would come up and out into 3-dimensional space. And now our curve would still be oriented this way. And Stokes' theorem is exactly the same as Green's theorem, but in 3-dimensional space. So Green's theorem related a 2-dimensional thing on the interior to a 1-dimensional thing around the boundary. Stokes' theorem is the same. It's just those 2-dimensional, 1-dimensional things are allowed to live in 3 space. So that's the idea of Stokes' theorem. OK, I'll turn this off and then do an example. So before we talk about Stokes' theorem, we'll talk about in the second half, we should just do more vector surface integrals, because we haven't actually done very many yet. So here's a vector surface integral. At the end of class last time, we derived the formula for doing a vector surface integral in general after we did a sort of a special case where things were a bit simpler. So we'll use that formula in this one. So imagine that you are wearing a little tin hat, like a conical tin hat, because that's a good thing to do to protect yourself if you're worried about bad things happening. And then you do a handstand, like you do, and so the hat becomes upside down. Well, it's a upside down hat, but it's sort of right side up for a cone. So here's the hat. And then you decide you're going to wear it in the vicinity of an electric field. So a really great way to do that would be if the power goes out, which it usually does at Swarthmore every time it snows or whatever, there's a big power generator. So maybe close to the power generator, there's an electric field. So you can go over and wear your little tin hat near the electric field. So suppose your hat is given by the surface z equals the square root of x squared plus y squared. So that's our usual cone. Another way to describe that is z equals r if you're in polar coordinates. And the electric field that is in the vicinity of your hat is E equals something like x z y z y. X z y z y. And we want to know, is the electric field generally flowing out of your hat or into your hat? So you have to pick an orientation for your surface. Let's decide we're going to pick an outward orientation for the hat. So the hat is given like this, and we are deciding that it has outward or downward orientation. So we want to know, so we want to compute the flux of E over the hat. So the flux of the electric field is just the amount that the extra electric field flows through your surface. So if this number comes out positive, which it will, I happen to know, that means that the electric field net points out of the hat. So if we had arbitrarily chosen an inward orientation, then our answer would come out the same except negative. And then we would know, oh, it points in the opposite direction. OK. So let's do this. We'll compute the flux of this electric field over our hat. So the first thing we need to do is set up a parameterization of the surface. So I'll remind you where this is going. Last time we derived that the double integral over your surface of your vector field, which here is called E, dot n ds, is the double integral over the region of your parameter space. Like in here, it's going to be r theta space of E of x of whatever your variables are, dot your cross product of your normal vectors, d one variable, d the other variable. OK, so I've left a few blanks because we don't know what our variables are yet. But that's the idea. We're going to plug this in. So the first thing to do is to parameterize the surface, the hat surface. So since it's basically a circular thing, let's use r and theta. So x of r and theta, move this over, x of r and theta. Let's see, it's a circular thing, so maybe x should be r cos theta, y should be r sine theta. Fine, and then we have to figure out what z is. One way to do it, well, z, whatever x and y you pick down here, you just plug it into the surface equation to figure out z. So our surface equation is the square root of x squared plus y squared, or just r. So our z is just r. Okay. Now, let's see. Now what we need to do is find normal vectors to the surface. Sorry, not normal vectors. Find tangent vectors. It's dramatic foreshadowing. We're going to use the tangent vectors to find the normal vector. So the way we do tangent vectors is we take a vector in the direction of r and a vector in the direction of theta. So let's compute them, and then we'll sketch them and see what they look like. So xr is the partial derivative of these things with respect to r. So cos theta, sine theta, 1. And x theta, we'll just compute it, is negative r sine theta, r cos theta, 0. OK, let's draw these in and see what they look like. So xr. OK, that xr means you hold theta constant and you increase r. So hold theta constant means don't go around the cone. Just stay where you are, the theta, and then increase r. So it would make sense that we don't go around at all. We just sort of go up the side of the cone. And in fact, that's what's happening here. This is like x, this is like y, and this is like 1. This is sort of like x, it's just without the r. It's in the direction of x and y and 1. So it's going out, away from the origin, and up. So this part tells you it's going outward, and this part tells you it's going up. So outward and up, that's this blue vector. Okay, x theta now. X theta says keep r fixed, don't change how far out you are in the cone, and just go around the circle. So that is just around the circle. It could be clockwise or it could be counterclockwise. Let's figure it out. Negative r sine theta, that's just negative y, and r cos theta, that's x. And we've looked at this vector field before, negative y comma x. It goes counterclockwise. So it looks like this green vector, I've put it in the correct direction. It goes counterclockwise if you're looking from the top. Okay, so these two vectors are tangent vectors to the surface, and what we need is a normal vector. So now we know this will be parameterized in terms of r and theta, and this will be dr d theta. Oops. Okay, so let's find a normal vector. We'll just do xr cross x theta. So usually I'd write this out I, j, k, and then these things, but they're already kind of in this nice orientation, so I can just do it right here. So cover up the first, take the determinant of this little matrix, 0 minus r cos theta is negative r cos theta. Then for the middle one, the negative of 0 minus negative r sine theta, minus 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 is minus, so I get negative r sine theta. And then for the last one, r cos squared theta plus r sine squared theta is r. Okay, so this is a normal vector to the surface. Let's check to make sure it goes in the correct direction, because we chose that we would have an outward downward orientation, so that's what we want. So this is negative r cos theta, that's like negative x, negative y, and z. So negative x, negative y means it's pointing in towards the origin. And z, this is a positive number, so it means it's going up. So this part tells us it's going inward, and this r positive thing tells us it's going up. So it's going inward and up. So if this is our cone, it's a bit hard to see inside a cone, but our vector is pointing inward and upward. So it's actually the inward pointing vector. It's not the one we wanted. So this is not the one we wanted. So actually we could have figured that out originally. We had xr cross x theta, and we actually even drew them in this picture. So if you do xr cross x theta, you take your fingers, put them in the direction of the blue vector. Good, some of you are doing it. You take them and you curl them towards the second vector, that's the green vector, and then your thumb points in the direction of their cross product. So we can see just from this it will be pointing inward. So that wasn't the one we wanted. So what we want is green vector cross blue vector. If you do that, green vector cross blue vector, it points out. It's what we want. So we want, in fact, x theta cross xr. And if you want, you could do the cross product again, but we know that the cross product, if you switch the order, it just changes the sign. It's the same thing, but in the opposite direction. So I can just change the sign on all these things and get r cos theta, r sine theta, negative r. And that's the one that we want. Yeah?
Sorry, can you explain again why you have to switch the order of the cross product?
Sure. So we want to switch the order of the cross product because at the beginning we decided that we wanted an outward orientation for our cone. So we want these vectors that go like outward and downward, these orange ones that I've drawn. That's the orientation we wanted. And then when we took the cross product to find our normal vector, well, we found that it's actually the opposite of the vectors we wanted. It was these ones that went inward and upward. That's what we got. Do I have another color that I haven't used yet? Purple. So this vector, this inward and upward vector, is actually the one that points into the cone.
How did we determine that we wanted an outward, downward orientation?
So
Is it arbitrary?
it's arbitrary at the beginning. So usually you're given it. Like, I would like my cone to have outward, downward orientation, please.
Okay.
So we were given it at the beginning.
Okay.
It's an arbitrary decision, but you're usually given it.
So say we go through the incorrect normal vector.
Yeah.
Is the only thing that gets affected at the end and just the sign.
Just the sign. That's it, just the sign. So if you like do it wrong, the only thing that will be off is the sign. In fact, if you want, yeah, you could go through with the whole opposite direction normal vector and then at the end change your sign. Yeah. Yeah, sure. Okay, so it turns out we want x theta cross xr, and that's why I resisted putting these in. Okay, so now we have everything that we need. So we want to find the double integral over the surface of this flux of this vector field. So let's write it down. Okay, one thing I didn't do, which is that when we parameter, I forgot to say which values of r and theta we wanted. So we want r between something and theta between something and something. So theta, I think, should go from 0 to 2 pi, so you go all the way around the hat. And then r, well, we know the hat, actually, I didn't even say that either. The hat is given by this for z from 0 to 1. You could make your hat as big as you wanted, but let's say it's just a 1 hat of dimension 1. So r also goes from 0 to 1 because r is the same as z. So now we want to take the dot product of E with the unit normal vector ds. So at the end of class last time, we figured out that if you find a unit normal vector, you're dividing by the magnitude of the cross product. But then if you do ds, you're multiplying by the magnitude of the cross product. And that these two parts cancel out. So that's how we figured out that all you need is you have to put your parameterization for your surface into your vector field and take the dot product with the normal vector that you get out. Okay, so let's do it. So this is the double integral over the region that we're interested in the r theta plane. So this is theta goes from 0 to 2 pi, and r goes from 0 to 1. Okay, E of x of r and theta. So we haven't used E yet, but E is our vector field that says how our electric field is going. So it's x times z. So x times z is r cos theta times r. So this is r squared cos theta. And that is x times z. Okay, then we want y times z. So that's r sine theta times r. So that's r squared sine theta for the y times z. Uh-oh. Okay, and then comma, our last thing is y, and y is just r sine theta. So there's the y. And we want to take the dot product of that with our normal vector, which we know the correct one is x theta cross xr. So after much rejoicing, we found that one. That is r cos theta, r sine theta, negative r. And we want to do that dr d theta. Okay, so now we've set the thing up. We know what our vector field is at each point according to r and theta, and we know the normal vector. So we can take the dot product of these things. So that's the integral from theta equals 0 to 2 pi, of the integral from r equals 0 to 1 of the dot product. So this is r cubed cos squared theta plus, this times this, r cubed sine squared theta plus, this times this, negative r squared sine theta. Negative r squared sine theta. And we want to do that whole thing dr d theta. Okay, cos squared plus sine squared is 1, and they have the same coefficient. So this is the integral from theta equals 0 to 2 pi of the integral from r equals 0 to 1 of r cubed minus r squared sine theta integral dr d theta. And now this is something you can do. Just have two terms. We can't break it up into a theta integral and an r integral because this term has both parts, so you just have to actually do a double integral. But it's something you've done before, and it comes out to pi over 2. Okay, so because it comes out positive, it means so E flows in the direction of the chosen orientation, which is out of our hat. So it might be that there's some bits of the vector field that are flowing in, and then some bigger bits that are flowing out, but net, the vector field is flowing out, the flux is flowing out. Yeah. Questions or ideas? All right. So I discovered in teaching this at 10:30 that I didn't have enough time to do both examples and then do an example of Stokes Theorem as well. So I'm going to skip the second example. I would just ask you to make a little modification. The cylinder is x squared plus y squared equals 9, but then I decided that that circle had radius 5. So you should probably just change the 9 to a 25. Either that or change all the radius 5s that appear below it to radius 3 so that it's consistent. Okay, so sorry about that. And we're going to skip that example just so that we can give Stokes' theorem its due. So, so Stokes' theorem is about relating vector surface integrals to the integrals around their boundary. So if you have, so first I should say what it means for a surface to have boundary. So a sphere doesn't have any boundary. But our conical hat, the boundary of the conical hat was just like, it's like the rim of the hat. If you took a sphere and you cut it in half, then that equator circle or whatever would be the boundary. If you took a cube, it wouldn't have any boundary, but if you poked a small hole in it, the boundary would be around the hole. So, so the boundary of a surface is just the curve that is on the edge of the surface. So when we talk about the boundary, we care just about the edge. So Stokes' theorem says that, I'll draw a picture for this, if you have a surface with boundary, now it might not have a boundary, like if it's a sphere, but if it does have boundary, it has boundary. Okay, so this one, here's our surface S, and then here's the boundary curve, which is denoted by boundary of S. This little partial derivative thing means boundary. So it says that if you want to take a vector line integral over the boundary, the vector line integral over the boundary of S of that vector field dot d little s, so this is the adding up the vector field around the curve, is equal to the double integral over the surface of the integral over the curl of f dot d big S, a surface integral. And that these are equal as long as the surface and its boundary curve are compatibly oriented. So as long as S and the boundary of S are oriented compatibly. Okay, so this is really fun, and but you know, most things that are fun are a little bit hard, right? Like your sport is fun because you have to practice. If it was really easy, it wouldn't be that hard. Like that game where you just click, and every time you click, you get a point. It's not that fun because it's not that hard. This is a little bit interesting, so we'll practice it a bunch of times. So oriented compatibly. What this means is, let's see. If you walk around the boundary of S with your head in the direction of the chosen orientation normal vectors, your left arm is over the surface. Okay, so here's what I mean. You imagine that you are in zero gravity or whatever, so you can stick to the surface. So you walk around the boundary. Now, if you wanted, you could walk up here on the other part of the surface, whatever, that's fine, but that won't help with figuring out the orientation. So the important thing is when you, let's see, you are a Swarthmore student, so you are red. You are on the boundary. So here you are, armless currently. And then if we were at the front, we'd sort of be pointing out toward the board. So I'm not going to draw us pointing down because that would be confusing. But you can imagine you are sticking out like this, out of the board. And at the back, you're sticking into the chalkboard. So that's the idea. And you want it to be that your left arm is over the surface. So you're holding out an arm, and you want this to be your left arm. So we have to decide, as this person's walking like their head is sort of going like this, and their arm is sticking out. Or maybe they're walking sort of like this, and their arm is sticking out. Do you want this to be their face, and this is the back of their head? Or do you want this to be their face, and this is the back of their head, so that their left arm is over the surface? What do you think? Should they walk left? Oh. I have decided, which I did not say, that for this surface, we are using the outward normal vectors. Okay, so our head is pointing in the direction of the normal vectors. What do you think? Should we be walking left to right or right to left? Yeah, left to right. Because you can imagine me sticking out of the board like this, and I'm walking along, and my left arm is over the surface. Yeah, so the compatible orientation to this outward normal vector is going along this way. Okay. So I have drawn a bunch of surfaces and boundaries and oriented one or the other, and I'd like you to put in either the normal vectors or the surface or the curve orientation for each of them so they're compatibly oriented. And talk to your neighbor. Go. Ready? Okay.
Let's go, Harsha.
Okay, so Harsha's gonna explain what's going on.
So for the first one, I think that, so you're standing up and you're walking along this direction, so your left arm is always going to be on the inside.
Talk out this way.
Yeah, so I think that this is the direction that you have to be going, because that's how, if you're pointing, like you're standing in the direction of the normal vector, your left arm's always over the surface. So that's what I thought made sense there. Here, I think.
How about we switch sides? You stand on that side and point this way. Okay.
Sure. So here, I think that it's kind of a similar thing. So the vectors are all pointing outward out of the dome. So there'd be like a normal vector basically like that. And if you were standing like basically out of the board, if you were walking in this direction, your left arm would be pointing over the surface. So that's why I thought that you have to be going.
Yeah. Oh, no. I'm just trying to visualize this.
So that's what I was thinking for this one. It's kind of the same thing because it's kind of like pushing this up to make a dome.
Nice.
So you keep walking similar direction. Here I thought that it's, so it's kind of the opposite because, so I think one thing that I was thinking about here is it's a dome just like this one. But if you turn this around, you'd actually have been walking in the opposite direction. So since we're walking the opposite direction, the vectors can't be outward pointing anymore. They have to be inward pointing. So those are the correct vectors. So if you imagine you're standing at the edge here, the inward pointing vector would be into the board. And then if you were into the board, you're walking in this direction. That's when, if you have your left arm out, you'd be covering the surface. That's what I was thinking. Yeah, exactly.
Okay.
That's what I was thinking for that. For this one, I had it like that, I think. So the normal vectors are pointing outward. So, somewhere here you have a normal vector, like in this direction, like pointing out from the lip. And so you're standing, jutting out from the surface. And if you're walking down, then your left arm would be over the surface. Your right arm would be outside the surface. So that's what I was thinking for that. And here you kind of have the same shape, but you've been given the direction. And I think there was kind of a similar problem there where, so you imagine yourself, for example, here, you're going up like that. So do you need to be standing upside down or towards us? And so, I realized that it's the inward pointing vectors that you need. It's hard to draw them in here. But something like that. Because then, if you're standing upright, then that's when your left arm is inside of the surface.
Yeah, nice, great. Yeah, thank you, nice job. Yeah, so I think these are kind of tricky to figure out. You have to imagine yourself moving around and your body pointing out of the board or into the board, and your arm, but they're kind of fun once you get them. Harsha mentioned this, that these are kind of the same, it's just, I forget what word you use, but maybe like pushed up or something like that. And I'd like to draw your attention to that these are actually kind of the same thing happening. So this, if we imagine that this is living in the plane, this is the kind of region that we applied Green's theorem to. It's just sitting in the plane, and our curl vectors were always pointing up because our vector field was always in the xy plane. Either if our curl vectors were pointing up, our answer was positive, or down, our answer was negative. So our orientation was always up. Now if you take this, and imagine it's kind of like a balloon on a circle, wire circle or something, and imagine that you blow into it from the bottom. Then you get this picture. And so the blue curve is still going around in this direction, as it is down here, but now all the normal vectors, which are just pointing up, are now kind of pointing out. Okay. On the other hand, suppose that if you take this thing, and now I kind of imagine that these normal vectors are like a koosh ball, all pointing up. Now imagine that you take this and you blow down through it. Well, then it looks like this. So the orientation is still going around in the same direction, but now these normal vectors have gone like that. And so they're all pointing in. So these are all three versions of the same picture, but if you imagine it to be stretchy rubber, you've got the flat one, the one pulled up, and then the one pushed down. Yeah. Yeah.
So is Stokes' theorem like the vector field surface integral version of Green's theorem? Like Green's is to line integrals as Stokes is to vector surface integrals? Can you say like that kind of like correlation between the two?
So they're very, very related, and I think they're even more related than that, because Green's theorem is secretly, actually it's a vector line integral around a curve, and it's relating it to what is actually secretly a vector surface integral over the surface. So it's like Green's theorem, you just take Green's theorem, which only lived in two-dimensional space, and then you just allow Green's theorem, the region, to be sitting in three-dimensional space. Like a little flat membrane in three-dimensional space. Just take it out of the plane and put it in three-dimensional space. And then you allow it to be curved. The surface to be curved and the line integral to be curved. So Green's and Stokes both relate vector line integrals to vector surface integrals, as long as you think about Green's theorem correctly as a vector surface integral. Yeah. Yeah. Okay, so this is compatible orientation. If you happen to mess it up and get the wrong orientation, the only thing that goes wrong is you get a sign error. So you might even be able to catch your error if you look at the sign of the answer and figure out whether it makes sense. But I think it's actually pretty fun to figure out the orientation. So, okay. So let's do an example of using Stokes theorem to do, Stokes theorem to do something. Okay. So, for example, let the vector field F be given by something, so negative y, comma, x plus z minus 1 times x to the x sine x, something yucky involving x, and then x squared plus y squared. And let our surface S be the part of the sphere. Let's just say the spherical cap, part of x squared plus y squared plus z squared equals 2, that lies above the plane z equals 1. Okay, so what on earth do I mean by this? Well, we have a sphere here whose radius is square root of 2, so square root of 2. And so if I went all the way to the top here, I would have z equals the square root of 2. But I'm not going to do that. I'm just going to go up to 1. So 1 is maybe right here, and I'm going to slice it off. So we get this. There's the boundary, and then our surface is this part. So there's S. There's our surface, our spherical cap. It's sort of like a yarmulke. It doesn't go around your whole head. It just sort of sits on top. We have outward orientation. So outward orientation. Okay, good. So compute the double integral over S of the curl of f dot ds. So suppose we wanted, for some reason, to integrate the curl. We wanted to know how the, let me use my right hand here, the axis of rotation was flowing through our surface. Okay, so method 1 is to just do it. Let's go. So f is this thing. So the curl of f is, we set up something. I'm going to write the bottom first. Negative y, x plus z minus 1, x to the x sine x, and then x squared plus y squared. And then we're going to have I, j, k, and then partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z. I wrote them in order to make sure I had space to write it. Okay, so what happens? Let's see. We take, well, one of the things we're going to have to do is take the derivative with respect to x of this business here. So for I, we do this thing, no problem. For j, we do this thing, no problem. But for k, we do the derivative with respect to x of this thing, which looks like kind of a mess. So it's going to be something, which I'm not going to compute, something else, which I'm not going to compute. And then the last thing is derivative partial with respect to x of x plus z minus 1, x to the x sine x. Maybe it's minus. Something involving that. We're going to have to do this derivative, which is a mess. And then once we do it, we're going to have to integrate it. So this seems like a bad idea. So this seems bad. Let's try Stokes theorem. Okay. So let's see if we can use Stokes theorem. Usually, well, this one is a little bit contrived so that it works out to be better with Stokes theorem. Okay, so Stokes theorem says that this thing that we want, this double integral over S of the curl of f dot d surface integral, is equal to the integral over the boundary of S of f dot d line integral, as long as the things are compatibly oriented. So let's make sure we orient our boundary correctly. I think we have an example picture right here. We have an outward normal, so our thing should go counterclockwise. So I'll just copy this onto here. So there's ds. So to orient s and ds compatibly, let's do ds counterclockwise. So counterclockwise if you're looking at it from the top. Yeah, if you're looking at it from the bottom, it would be clockwise, so we won't talk about that. That would be confusing. Okay. Okay. So now we need to actually compute this integral. So vector line integrals are something we haven't actually done for a few days. But the first thing we do in a vector line integral is we parameterize the curve. Just like for a surface integral, which we've been doing, we parameterize the surface. So let's parameterize the boundary curve, boundary of S. Okay, so, we're going to have to figure out what it looks like. So it's the top of a sphere. This is just a cross section, side view. We cut it off with the plane z equals 1. So this is 1. Here's the plane z equals 1. And then the radius of our sphere was the square root of 2, and this is a right triangle. So the radius of our spherical cap here that we care about is just 1. Because it's a, isosceles right triangle. Okay, so the boundary curve has radius 1, and it's oriented counterclockwise. So this is this curve from a side view, which is a circle. So perhaps we should let x of t, or theta, what did I do? I did theta, is just cos theta sine theta. Because that's a circle of radius 1 that goes counterclockwise, our old favorite. But in fact, it's not just in the plane. That would be if it was circling around in the plane, but its z value is up a distance of 1. So this has to be comma 1, because it's doing this up on the plane z equals 1. Okay, and then we'll need our derivative. So x prime of theta is negative sine theta cos theta 0. And now I think we can compute this thing. Okay, so the thing that we want, the double integral of the curl over the surface, is equal to the vector line integral over the boundary, which is equal to, let's figure this out. So theta should go from something to something. I guess we want to go all the way around, so 0 to 2 pi, of our vector field of our parameterization. So x of theta dot x prime of theta d theta. Okay, sort of a blast from the past because we haven't worked on that for quite a while. So now let's plug this in. So we're going from theta equals 0 to 2 pi, f of x of theta. What on earth was our vector field? So let's maybe plug that in. So f of x of theta is cos theta. Okay. I want you to be able to see it at the same time. Maybe you can see it. Okay, I'll write it again. F is negative y, x plus z minus 1 times something hard, and then x squared plus y squared. So on this circle, negative y is negative y, fine. Z equals 1, so it's x plus z minus 1 times something is just x. And then this circle has radius 1, so x squared plus y squared is just 1. So on our curve, f is just negative y comma x comma 1. So f of x of theta is negative y, so negative sine theta, comma x, which is cos theta, comma 1. And we're going to dot that with x prime of theta, which is negative sine theta, cos theta, 0, and then take that d theta. So this part was negative y, this part is x, and this part is 1, because over here we did some scratch work to figure out that when we plug in this particular curve, our vector field gets a lot simpler.
What are we plugging into what?
So we plugged in x of theta into our vector field, into our original vector field equation, which I wrote far there over there on the left. So negative y is just negative y. So here it is. It's negative y. It's x plus z minus 1 times some complicated thing. But z is always just 1 on our curve. So 1 minus 1 is 0. Okay. And then to finish this up, we go from theta equals 0 to 2 pi. Negative sine theta times negative sine theta is sine squared theta. Cos squared theta times cos theta is cos squared theta. Plus 0 times 1 is 0 d theta. So it's the integral from 0 to 2 pi of 1 d theta, which is 2 pi. So that was a lot easier, and it tells us that our vector field generally points out in the same direction as our chosen orientation. All right, thanks everyone.